Hello everyone, welcome to Algebra 2B. This is for week 11, starting to learn about trigonometric identities. So week 11, we're almost done with the second half of Algebra 2B. Make sure you're going over the stuff you need to. Use this video to help you work on the paper pencil problems and the quiz in Canvas. Here's what we're going to be learning this week. If I give you various trig identities, we're going to be proving that they are true. We're going to dig into those trig ratios again, sine, cosine, tangent, opposites, adjacents, and we're going to use the Pythagorean theorem to really understand how trig functions work together. If I give you one trig value, we're going to use our trig identities to find all the other trig values, secants, tangents, cosines, cosecants, all that stuff. We're going to simplify algebraic expressions that involve some trigonometry using these trig identities. If I give you a new trig identity, we're going to verify if it's true or not. And then finally, we're going to use all our abilities to do algebra with trig to start learning how to solve more equations. So this week's a little bit more nitty-gritty. Last week was more graphing and modeling with trig functions. This one's more just the sheer algebra of being able to rearrange and simplify different expressions. So again, think about where we've come from. With all of our trig, we started by looking at triangles, right? Right triangles and trig ratios, how to solve for unknown sides and draw all sorts of triangles. Then we applied those triangles with the unit circle and learned about radians, learned about measures around. Then we applied the unit circle and all those triangles to actually see that we can make functions, these little wavy lines, right? What we're going to move next is digging kind of full circle back into triangles and trig ratios to look at more complicated trig expressions. So what is a trig identity? When we use this word, a trig identity. A trig identity is a true statement using trig functions in the form of an equation. And this week we're going to prove a bunch of them and then show how we can use trig identities to rewrite expressions and ultimately simplify and solve algebraic expressions. So here's some of the basic ones we already know, we've already looked at. We have reciprocal identities, right? If I give you sine of an angle, we know that that is the same, it's equal to 1 divided by the cosecant. Or this reciprocal, right? Cosecant is 1 divided by sine. Cosine has its inverse or reciprocal trig identity, cosine and secant, tangent, cotangent, and we've already known about those, right? And we're going to learn some other ones here. So let's prove that the following one is true. Is tangent of an angle really equal to sine of an angle divided by cosine? So we've already kind of used this. We've been running with this assumption in our class. But let's actually prove that it is true. Where does that come from? Tangent is equal to sine divided by cosine. Well, let's think about my triangle, right? All right. So there's my right triangle. And here is my angle. Based on this angle, this side is the opposite side. This side is the adjacent side, kind of orienting ourselves. And this side is our hypotenuse side. It's the longest side. And we know that sine of that angle is equal to the opposite side divided by the hypotenuse. We know the cosine of that specific angle is equal to the adjacent side divided by the hypotenuse. And we know that tangent is the opposite divided by the adjacent. So these are our main trig functions right here. So now how do we show that tangent, cosine, and sine are related? Well, let's think about this right here. Let's take sine divided by cosine. And using the fractions that we know, that's the opposite divided by hypotenuse, that's the sine, divided by the adjacent divided by the hypotenuse. All right, so that makes sense right there. Just substitute what the ratios are in for each function. If I rewrite it a little bit differently with division, opposite divided by hypotenuse, that's the numerator, divided by the adjacent divided by the hypotenuse. And now this looks really familiar, right? When we divide fractions, what we do is we turn it into a multiplication problem with the reciprocal. So let's make it the opposite divided by the hypotenuse multiplied by the reciprocal, the hypotenuse divided by the adjacent side. Well, what do we have here now? Well, now things actually simplify pretty nice. We multiply across the top, multiply across the bottom, but we see that the hypotenuses, that side length, is actually going to divide out. They're common factors in the numerator and denominator. So, if we start back from the beginning, what do we see? Sine of an angle divided by the cosine of an angle is equal to the opposite divided by the adjacent. And that's where we get tangent is equal to sine over cosine. Sine divided by cosine. We showed it was equal to the opposite side divided by the adjacent side for all triangles, which is the same thing as the tangent. And there we go. We just have proved this following identity, and we can now use it wherever we would like in our mathematics. Pretty good, tangent identity, right? There's also a Pythagorean theorem identity. Prove that this following is true. Is the sine squared of an angle plus the cosine squared of an angle, is it truly equal to 1? All right, well, let's play around with this. So I'm going to draw my triangle. Right over here, got my right triangle. And we want to show, we do know that a squared plus b squared plus c squared, that's our Pythagorean theorem, right? That whatever a squared plus b squared, if I square those and add them together, it equals my hypotenuse squared. But now we got to figure out how to apply that to all my trig stuff over here. Okay, so if I think about it with trig angles, there's my angle, there's the opposite, there's the adjacent, there's the hypotenuse. All right, so what do we got? So we do know we got these trig functions right here, right? We know the sine of an angle is the opposite divided by hypotenuse. Well, if I multiply both sides by the hypotenuse, the sine of an angle, if I multiply both sides by the hypotenuse, we can rearrange this into, the hypotenuse times sine of the angle is equal to the opposite side. And that opposite side is the same in this case as b. So I'm going to substitute the hypotenuse times sine of the angle in place of b. So this is all squared. With that same logic, the adjacent side I can rewrite as the hypotenuse times cosine equals the adjacent side. Right? Because cosine is adjacent divided by hypotenuse. If I multiply both sides by the hypotenuse there, I can substitute all this in for A, the adjacent side. So now we've got the hypotenuse times cosine of the angle squared. Those two squared, that's A, that's B squared, should add up to equal the hypotenuse squared. All right, but we kind of see some nice things going on here, right? Let me write this a little bit differently. Hypotenuse and the cosine of the angle are both squared, so let's write it as the hypotenuse squared times the cosine squared of the angle plus the hypotenuse squared times sine of the angle squared equals the hypotenuse squared. And now hopefully you see there's some nice things that divide out. If I divide both sides by the hypotenuse squared, what do we have left? Well, the hypotenuse squareds all divide out. And I'm left with cosine squared of some angle plus sine squared of some angle has to equal 1. And there we go. We've just proven the Pythagorean theorem identity. Take any angle, the cosine squared plus the sine squared always is going to add up to equal 1. All right, we got one more identity here, our cofunction identity, right? Prove the following is true. We've already kind of looked at this. We know that sine and cosine are really the same values, they just have a different horizontal shift. But how can we prove it? Well, I'm going to go flip over to our unit circle and let's take a look at something. Pi over 2, if I translate, that's in radians, that's the same as 90 degrees, right? So all this is saying is if I shift by 90 degrees, the sine actually turns into the cosine. So let's take a look at that. We should be able to see this on our unit circle for the exact values. All right, so let's switch over here. All right, so here we are at our Desmos calculator. We've got our sine graph. Let me go ahead and add cosine. And our property says sine and cosine are the same if we apply a shift. So let's take the sine. Let's actually shift it by 90 degrees. I'm going to move it, I'm going to subtract it by 90. So moving it to the right didn't do it, but let's move it to the left by 90. Oh, I forgot I'm in radians. Let's do it by pi over 2. And there we go. So there's shifting it by 90 degrees, or pi over 2 radians. And we can see that they're now identical. Our graphs are the exact same functions. I can switch to table view. And there we go. At -2, -1, 0. We're getting the exact same values. So I can see this with my graph, that doing a phase shift of pi over 2. And again, I can flip it over and say, well, instead of x plus pi over 2, I can make it match to say pi over 2 minus x. That'll still give me the same exact thing. Same phase shift. And thus we can kind of run with it. So anytime you have a sine, if there's a phase shift or a horizontal shift of pi over 2, we can replace it with the cosine. That's an identity. So we can switch around sine and cosine if that helps us anywhere with our actual functions. If we're simplifying and working with different expressions. All right, let's go back to our PowerPoint. So we saw that, yep, we proved graphically, we could see that the same exact graph, same exact table, same exact values when we apply this horizontal shift to get sine equal to cosine. All right, what about some negative identities? Again, we're looking at all the different ways we can write and rewrite and work with sines and cosines. How about this one? The sine of the negative of an angle is equal to negative sine of an angle. And then we also have this one, same thing for cosine. How are those true? Well, let's kind of take a look at some triangles and see if we can understand some stuff here. So we know if I draw this triangle here with our unit circle, there's my radius of 1. Sine is always my y value, and cosine is always my x value. And if this is 30 degrees, then let's see, cosine, the sine is 1/2, and the cosine is square root of 3 over 2. And actually, let's switch over. So we're going to do these. Let's switch over to looking at our unit circle, and we'll actually see this go on here too. All right, here I am at our unit circle. So what do we see? Well, here's what we did. 30 degrees, square root of 3 over 2, 1/2. And now remember, our property was the sine of the negative angle. So sine of negative 30 degrees would be right here, is the same as negative sine of the positive angle. So what does that mean? So that means sine of 30 degrees is 1/2, but sine, if I go backwards 30 degrees, is negative 1/2. Well, these are the same values, just one is positive. So if I made this 1/2 negative, it would be exactly the same. Sine of 45 is the square root of 2 over 2. Well, negative square root of 2 is right here if I go in a negative 45 degrees. So you can see square root of 3 over 2, negative square root of 3 over 2, 1, negative 1. If we go forwards in a positive angle, the sign is exactly the same. If I go negative at same angle measure, only one's positive, one's negative. So that first identity is true. The sine of an angle is always equal to the opposite of sine of the negative angle. All right, but what about cosine? Well, cosine of 30 degrees is square root of 3 over 2. And if I go negative 30 degrees, it's also square root of 3 over 2. So cosine is kind of funny in that if you go the opposite angle measure, you end up with the same cosine. Cosine of 60 is 1/2. Cosine of negative 60 is 1/2. Cosine of 150 degrees is negative square root of 3 over 2. Cosine of negative 150 degrees is also negative square root of 3 over 2. So for the cosine, positive, negative angles, they're going to give you the same exact cosine. So we were able to see these exact things from the graph, right? If you have a triangle, sine is always your y value. So this was 30 degrees that way. If I go negative 30 degrees, it's the exact same length. It's just positive instead of negative. So yeah, so sine at this point, if I take the opposite, it's the same there. Cosine just has the same value, whether it's positive or negative. All right, well, let's find some exact values. So we dug in, we looked at some identities. How do we use some of these identities now? So I tell you, we got the secant of some angle equals negative 4. Now we could do inverse secant on our calculator and we could figure out what that angle is. But as soon as we do that, using the calculator gives us the approximate angle measure. It gives us like some degrees with a long irrational number. But what if we want to find exact trig values? Well, we can use our Pythagorean theorem and we can use our trig identities to help us do that. So let's think about this here. So if secant of some angle is equal to negative 4, the secant is the reciprocal of cosine. So what that means is the cosine of that angle is negative 1 over 4. It's the reciprocal. So there we go. We already got two. So we have secant, we got cosine. How do I find sine and tangent and all that stuff now? Well, let's remember that the cosine is your adjacent side of a triangle divided by the hypotenuse? Well, let's draw a triangle then. So here we go. There's my best right triangle, and there's my angle. I don't know what the angle is, but I do know that the adjacent side is 1, and the hypotenuse is 4. And in fact, actually, if I'm with -1, let me do this here. I'm going to draw it on here. So we're going to go -1, now hypotenuse of 4. We can just kind of use this to help us see it. So a hypotenuse of 4, and then we have an adjacent side of -1. All right, let's find some other trig values here. We can use this side, which is the opposite. We can find it by using the Pythagorean theorem. A squared plus b squared equals c squared, right? So 1 squared plus some unknown opposite side, we're going to call that b squared, has to equal 4 squared. Well, that's 1 plus b squared equals 16. 16 minus 1 means b squared equals 15, which means that my opposite equals the square root of 15. That's this side right here, square root of 15. Okay, so now we can find all of our trig values, now that we got all three sides. So the sine of the angle is the opposite divided by hypotenuse, right? So that's going to be the square root of 15 divided by 4. If sine of that angle is square root of 15 over 4, then cosecant of that angle, the reciprocal of the sine, is going to be 4 over square root of 15. How about tangent? Tangent of the angle is the opposite divided by the adjacent. So that's going to be the square root of 15 over 1. And then cotangent is going to be 1 over square root of 15. Again, the reciprocal. So now we've got 1, 2, 3, 4, 5. We've got all of our 6 trig values based on just knowing what the secant was. Notice I still don't know the angle, but we found all the trig values. Now, what if I want to double check it, right? What if I don't believe it? Let's actually check this out on a calculator. So we can do some things and estimate some things and use our calculator to check our work. So let's go over there and do some math there. All right, so what did we know? We knew the secant of an angle was -4, right? So if I go to my functions and I go to inverse secant of -4, and let's just go switch to degrees to help us out. It looks like that angle was approximately 104.47 degrees. Well, now let's check some of our values, right? We said the sine of the angle, sine of 104.4775, we said that that sine value had to be equal to the square root of 15 divided by 4. Well, what do we see? We have the sine of the angle, and again, we kind of are doing our best estimate for the angle there, but we get 0.9682458365552. But look at this, the square root of 15 over 4 is also that same value. I like that, right? This is exact. I like square root of 15 over 4. I don't like irrational numbers that I have to kind of round to work with. But we just showed that, yeah, when we worked backwards and we found that angle, square root of 15 over 4 was true. What about tangent? Tangent of 104.477512.186. We got that tangent value. Well, the tangent we said was just the square root of 15. And we get the same 3.87298, 3.87298. We get pretty much the same thing. Here we start to see some irregularities because we're using these irrational numbers and our calculator just can't be exact with them. But this square root of 15 is exact. Now, why is this one negative? Why is this one positive? Well, we knew the secant was a negative number, which means the cosine was a negative number. And tangent is sine divided by cosine, right? So if you have sine divided by cosine and sine is positive and cosine is negative, then our tangent should be negative. So this would actually have to be a negative number as well. But there, this shows us these values we calculated, square root of 15 over 4, square root of 15, from the Pythagorean theorem are exact trig values. And you can use the Pythagorean theorem to find your sine, cosine, tangent, all the other trig values in an exact way. All right, so we got all our trig identities. We can use trig identities. Let's go simplify some expressions and show how to use this stuff with some algebra. So here we go. We've got cosine squared of x, tangent squared of x minus 1, all divided by cosine squared of x. I want to simplify this as far as I can. Make this mess of trigonometry nicer to work with. So how do we do that? Well, again, I want to use trig identities. I want to look for things that I know that I can rewrite. So what do we got? One thing I know that is tangent is really sine divided by cosine. And if I'm multiplying by cosine, but tangent is really divided by cosine, I can see that I might be able to simplify some things out there. So I'm going to rewrite this as cosine squared of some angle times, and we're going to replace tangent with, or tangent squared is the same as sine squared divided by cosine squared. And then I still have the minus 1, and that's still all being divided by cosine squared of some angle. Now this helps me out, right? Because I have a cosine squared times, but then I'm dividing by the cosine squares. These divide out, leaving just sine squared of some angle minus 1 over cosine squared of some angle minus, there we go. It's a little bit simpler, right? But now I'm looking at things, and I have a Pythagorean theorem identity, right? Remember, sine squared of an angle plus cosine squared of an angle have to add up to make 1. Here I've got sine squared of an angle minus 1. And so if I rearrange this thing, if I minus 1, and minus cosine, I can rearrange this into sine squared minus 1 equals negative cosine squared of some angle. So let's do that. Let's substitute that in place here. So we switch pen colors. So now we've got, instead of sine squared x minus 1, I'm going to replace that with negative cosine squared divided by cosine squared of some angle. I always forgot to put that x. Well, now we're getting somewhere. We're getting somewhere really nicely. The cosine of some angle and then the cosine of some angle, they're going to be the same angles. So it really just turns into negative 1 over 1, or just negative 1. There we go. We simplified this expression out, and all this is just the same as negative 1. Now, while you're doing expressions, we can check them out and just test them using our Desmos calculator as well. So let me show you that. So we want to show that this really does simplify to make negative 1. So all right, so I'm going to exit out. Here we are in our calculator. So the expression was for all values, but let's just put in a value in for x and see if it actually works out. So we have a fraction. We had the cosine, I'm just going to put 48 degrees. Cosine of 48 squared times the tangent of 48. I forgot to put parentheses around it. Now I'm kind of showing this to you too because the way you see your textbook write cosine squared, they put the squared in between, like the cosine squared and then the 48. But if you use your Desmos calculator, you have to put the trig angle in parentheses and then square the whole thing, just like I'm showing you. So this is the same as cosine squared of 48, is the same thing here as cosine of 48 squared. And then we had a minus 1. Now I'm just putting 48 in for x as a quick, dirty way to check that things work out. And we're dividing it by the cosine of 48 squared. Well, there we go. We put 48 in, and what does it all equal? It all equals -1, just like we showed. What if I put in 150, 152? Let's try a different angle and see if it works. There you go. Again, it simplifies to -1. So when we simplified it for any angle and said this is the same as -1, I'm feeling pretty good about it. I checked a couple angles on my calculator and it seems to work. So you can use this as you're working with rewriting expressions. Whatever you simplify to should be an equivalent expression to what you originally had, and you can use your calculator, put in some real values for the angles to help you check it out. All right, you're going to have some problems where you want to verify other identities. So besides simplifying, verifying means just showing it's true. So here's a statement. We say if I take the sine of an angle minus the cosine of an angle and square it, and add the sine of an angle plus the cosine of an angle and square it, it equals 2. So it sort of looks a little bit like the Pythagorean theorem, but it's not. It's kind of different too. But we want to show, is this true for any angle? That's what we call verifying other identities. So what I want to try and do is simplify or show that it's true based on other things that are true. So let's do some algebraic rearranging and see what we can come up here. So squaring it, I can think of this as a binomial squared. Use the FOIL method, and this is a binomial squared. And if I do that, what I'm going to have is, think of this as like x plus 5 squared, right? We can rewrite that as x plus 5 times x plus 5, and then distribute property, first outer, inner, last two, all that stuff. We're going to do the same thing. I'm just going to do that with sines and cosines. So if I do this, I end up with sine times sine, or sine squared of x. I'm going to have a sine times a cosine and another sine times a cosine, but negative. So there's going to be -2 sine of x times cosine of x. And then I'm going to have a cosine times another cosine, but they're going to be positive. And so I have a positive cosine squared of x. So there we go. We FOILed this binomial out, and we would get this. Plus, now we've got this binomial here to FOIL out. So let me go do that. That would be the same thing, only instead of -2x, I would have a plus 2x in the middle. So we would have sine squared of x plus 2 of them, 2 times sine of x cosine x, and then plus another cosine x squared. And it still equals to 2. So we use some polynomial stuff, some multiplying binomials to expand it out and see if we can start rearranging some parts in this thing. We see some things work out nice. I've got a -2 times sine x cosine x, and I've got a plus 2 times sine x cosine x. Those are going to cancel out to 0. I've got a sine squared of x plus another sine squared of x, and I got a cosine of x plus another cosine of x. So I'm going to write that as 2 of them, 2 times sine squared of x, and I've got 2 of the cosine squared of x's, and it equals 2. Now what's jumping right out of me here is I've got everything multiplied on both sides by 2. So I'm going to divide everything by 2. And we've got sine of x squared plus cosine squared of x equals 1. This is true. We know this is true. This looks like something we've seen before. This is the Pythagorean theorem identity. So if we took this and showed it's the same as this, then this identity is also true for any angle that we want. We just verified this whole statement right there. Hopefully you're kind of getting the idea of how some of these identities work. Hopefully you're getting the idea of how we can use sines and cosines and tangents. We can rearrange things and simplify things all with how these trig functions are related to each other. Lastly, I want to show solving an equation with more than one trig function in here. This one's going to be pretty straightforward. But again, the best thing you can do is just get in and practice and do some stuff yourself here. So let's solve the following. We've got 5 times the sine of some angle minus 2 is equal to 2 times the sine of some angle plus 4. And we want to figure out, well, what is that unknown angle? Well, just like we solve any other equation, I want to try and isolate x by itself. So to do this, I'm going to add 2 to both sides first. Minus 2 plus 2, those go to 0. So now we've got 5 times the sine of some angle equals 2 times the sine of some angle plus 6. I've got multiple trig functions, but I can watch this. I can subtract 2 times the sine of x from both sides. This goes to 0. Now I've got 5 times the sine of x minus 2 times the sine of x is giving me 3 times the sine of x equals 6. Now I want to get x by itself, so I'm going to divide both sides by 3. Sine of some angle is going to equal to 2. And finally, I use my inverse trig. I'm going to take the inverse sine of both sides. So my unknown angle is going to equal to the inverse sine of 2. All right, let's go to my Desmos calculator and actually calculate now. What is the inverse sine of 2? All right, here we are. Let's pull out a keyboard, go to functions. Inverse sine is the arc sine of 2. And, oh, we have undefined. What does this mean? Well, this is saying that there is no solution. So when I try and figure out what angle, where I take the sine of that angle, is going to equal to 2, apparently there isn't one. Well, this makes sense, right? Think about the unit circle. The unit circle starts at 1, goes up to 1 for sine, and then goes down to -1 for sine. And sine never gets bigger or smaller than 1 or -1, right? The sine of 90 degrees is 1, but it doesn't get any higher than that. The sine of 270 is -1, it never gets any lower than that. So if we're trying to find an angle such that the sine of that angle is 2, we're completely outside of the unit circle. It's undefined. So we solved this, but what did we see? There is no solution. So sometimes you'll solve it. You'll take the inverse sine or the inverse of whatever at the last step, and you'll get a solution. You'll get an angle. But in this case, there is no solution to that problem. All right, so what did we do? We did a lot. We did a lot with trig identities. We proved a few of them. We really hit the Pythagorean theorem. We really hit the signs, the opposites, the adjacents, the hypotenuses. We did ratios. We showed how to find exact trig values using the Pythagorean theorem. We did some simplifying expressions. And we did solving and finding new trig identities. All this stuff, it's some really, really good stuff here. I want to show you one more thing, a good resource for you. Hold on a second, I'm going to open up our Canvas class, and I want to show you a resource that'll be helpful as you're doing all of this. All right, here we are in our Algebra 2B class. I want to show you we're working our way through week 11. If you go to the week 11 module, I've got in for you here a trig math handout. It's just a PDF. I want to show you what it is. If you click on it, I can download it, but it's also going to pop open right here. I would definitely download it and have it on your desktop. But what I did is I listed out every single trig identity and formula that you may want. Well, actually, I borrowed it. It's from this campus right here. But there's all your reciprocal identities. There's all of our tangent sine over cosine and ways to write all that. There are our Pythagorean theorem identities, sine, cosine 1, There's some also interesting other Pythagorean theorem identities. These come straight from this sine cosine one. There's the Pythagorean theorem identities in radical form. So this would be if we square root both sides and solve for sine, tangent, cosine, etc. There's some cofunction identities. Again, these are the ones where we took a horizontal shift. We look at graphically how they were the same. Sine and cosine were the same if you had a 90-degree shift. There's the odd even identities that we looked at, depending on if things were positive or negative. There's some stuff with phase shifts and periods. We looked at that before. There's also some stuff where we're going to get into for next week when we finally get into sum and difference formulas and some other different things. So use this. There's a unit circle on here that's a reference for you if you want to. There's your right triangle definitions, hypotenuse, adjacents. There's also your exact trig values. So if you want to find those special angles and those special square root of 3 over 2s, square root of 2 over 2s, etc. All these may be helpful for you as you're doing trig, especially this week and next week. So have that out, make that available for you. Use that to refer off of as you're working on getting better at this stuff. All right, I look forward to working with you. Let me know if you have any questions for week 11, and I'll talk to you guys all later.